All right, let's jump right into this explainer and unpack the invisible brains powering our entire digital world. Whether you're watching this on a phone, a tablet, or a laptop, you are living through one of the most dramatic shifts in computing history. And, to truly grasp the magnitude of what's happening right now, we really need to understand the fundamental architecture that makes our devices think.
But before we get into the billion-dollar corporate slugfest, we have to ask ourselves why the very foundation of modern computing is shifting right beneath our feet. I mean, for decades, one architecture ruled our desktops and laptops with an iron fist. But now, a completely different approach, one born from the strict battery-saving constraints of mobile phones, is taking over everything from lightweight laptops to massive data-crunching supercomputers. So why the sudden shift? Well, that's exactly what we're here to find out.
Here's our roadmap for today. We'll start with Section 1, Meet the Computer's Brain. Then 2, Fetch, Decode, Execute. 3, Understanding Instruction Sets. 4, the ARM versus x86 rivalry. 5, Apple's big disruption. And finally, 6, the future of computing. Let's get to it.
Section 1. Meet the computer's brain. So, what exactly is a CPU?
When you compare a modern microprocessor to a standard dime, the sheer scale of the engineering is just wild. This tiny physical chip, literally smaller than a coin, is packed with billions of microscopic transistors. It acts as the core engine of your device, sending out signals to control every other part of the computer. It's almost exactly like how a central nervous system controls a human body. It's the absolute heartbeat of your machine. At its core, a CPU is essentially an incredibly fast electronic machine. No moving parts, just built entirely out of logic gates. It works its way through a massive list of instructions, relying on an internal clock measured in gigahertz. To put that into perspective, when we talk about a 3 gigahertz processor, we're talking about a chip pulsing through 3 billion cycles every single second. It is mind-bogglingly fast, taking your keystrokes and clicks and turning them into immediate digital reality.
Moving on to Section 2. Fetch, Decode, Execute. The instruction cycle.
Think of this process like an ultra-high-speed factory assembly line. The CPU just repeats a universal 3-step cycle hundreds of millions of times per second without ever taking a break. First, it fetches an instruction from memory, grabbing the raw material it needs. Second, it decodes that instruction via a binary decoder to figure out exactly what task needs to be done. And third, it executes it, performing the actual math or logic operation. Fetch, decode, execute. Over and over again in a seamless, invisible dance that powers every single app you use. What's really fascinating is mapping this concept onto actual physical hardware. If you look closely at the surface of a real Pentium chip, you can physically see dedicated zones designed specifically for fetching, decoding, and executing data. It's not just abstract software floating in the ether, right? It's physical geography mapped out on silicon. Every microscopic sector has a highly specific job in that assembly line. All right, Section 3, Understanding Instruction Sets. Basically, the CPU's manual. Now that we know how the physical assembly line works, we have to figure out what language these machines are actually reading. Every CPU needs a manual to translate software code into hardware actions. We call this the Instruction Set Architecture, or ISA. You can think of the ISA as the foundational language of the chip. The specific type of manual it uses completely defines its identity, how it interacts with software, and, crucially, how efficiently it does its job. And this brings us to the great divide in processor design. On one hand, you have CISC, or Complex Instruction Set. Imagine a heavy-duty crane. CISC performs heavy lifting, doing complex, multi-step tasks using just a single instruction. It's super powerful, but it's complicated and can use a lot of energy. On the other hand, there's RISC, or Reduced Instruction Set. Picture a fast-moving conveyor belt. RISC uses simpler, highly uniform instructions. Sure, it takes more instructions to finish a complex task, but it moves them with lightning-fast, predictable efficiency. Section 4, the ARM versus x86 rivalry, a massive clash of philosophies. This isn't just a battle between companies. It's a fundamental clash of engineering. Traditionally, the landscape worked like this. x86 chips, made largely by legacy giants like Intel and AMD, relied on the complex CISC architecture. They were high-performance beasts that powered heavy-duty PCs and servers, often relying on discrete, separate components for memory and graphics. That meant data had to physically travel further to get processed. ARM, however, went the RISC route. And here's the real kicker. ARM doesn't even manufacture chips. They license their ultra-efficient designs to companies like Apple and Samsung, who then tightly integrate everything, the CPU, the graphics, the memory, onto a single system on chip, or SoC. This architectural difference is absolutely huge. ARM's design practically solved the mobile phone dilemma overnight. I mean, when you build a smartphone, you need massive computing power to run high-end apps, but you absolutely cannot afford to melt the user's battery or literally burn their hands while they hold it. ARM provided that golden balance of performance per watt. It gave you the power you needed, but completely sipped battery life compared to the power-hungry x86 chips plugged into the wall.
Section 5. Apple's Big Disruption. Enter the M-series chips.
For the longest time, x86 owned the heavy computers on our desks, and ARM owned the phones in our pockets. But Apple sent absolute shockwaves through the industry when they ditched Intel's x86 chips and introduced their custom ARM-based M-series chips for MacBooks. They proved that ARM could not only run heavy-duty laptops effortlessly, but it could do it while doubling battery life. So why did it work so well? First, vertical integration. They control the silicon, the hardware, and the software. Second, they built a brilliant translation layer called Rosetta 2. This software translated old x86 instructions into ARM instructions on the fly, meaning consumers could run all their old apps and barely even notice the switch under the hood. Apple really pulled this off because they function like a solid, unified pillar of vertical integration. They had the ultimate power to issue a do-or-die mandate to their developers. Adapt your software to ARM or get left behind. Meanwhile, Windows and their manufacturing partners were much more like a messy pile of puzzle pieces. Because they lacked that strict top-down control over the hardware and software ecosystem, developers were a lot slower to rewrite their apps, the consumer messaging was fragmented, and early attempts at ARM-based Windows laptops really struggled to match Apple's seamless execution.
Which brings us to Section 6. The future of computing. The boundaries are totally blurring.
Let's wrap up by looking at where this trillion-dollar arms race is heading next, because the dust is definitely not settled. To survive, both sides are aggressively stealing each other's best moves. x86 champions like Intel are shifting away from separate components and adopting those highly integrated system-on-chip designs to save battery life and bump up efficiency. Meanwhile, ARM isn't just staying in phones and MacBooks anymore. They are pushing heavily into massive data servers, supercomputers, and directly challenging the Windows PC space again with huge help from hardware partners like Qualcomm. So we end on this question. Is x86 truly on its way out, or is it just evolving to meet a brand new standard? With ARM continuously expanding its reach into every corner of computing and the boundaries of efficiency being pushed every single day, what do you think the brain of your next computer will look like? Something to think about the next time you open up your laptop or scroll on your phone. Thanks for joining me on this explainer, and keep learning.